Okay, so for the second thing I want to talk about is how is magnetic field being created or being produced lah. Alright. So okay, so before I talk about magnetic field, let's talk about the gravitational field. If you have a mass of 1 kg, right? Yeah, this 1 kg will create a gravitational field in this particular direction. So the gravitational field is always attractive, hence your field lines will always be pointing towards the center of the mass. Okay, so if you have a stationary charge, in this case a proton, so you are stationary, this electric field will be pointing outwards. Okay, pointing outwards of the proton. But what if you have a moving charge? A moving charge will produce not just a electric field, it will also produce a magnetic field. Okay, so that's why a current or moving charge will produce a magnetic field. If you put a compass on top of a wire, be it on top of the wire or be below the wire, the compass will deflect because it sense or it detects some magnetic field created by the current, right? And the direction of the magnetic field can be determined by what we call the right hand grip rule. Yeah, okay. So if we look at the case of a long straight wire, so long straight wire carrying a current, not magnetic field. This long straight wire carrying a current will create a magnetic field, right? And you need to use your right hand grip rule to determine the direction of your magnetic field. Okay, so for your right hand, you need to put in this orientation. Okay, where your thumb is in the direction of your current and the four fingers are curling, right? Okay, in this long straight wire, our four fingers are curling in the direction of the magnetic field. Okay, so if you curl, and you will notice that you will have a magnetic field in this particular direction. Okay, in this particular direction. Hence, if you put a compass near the current, it will point in this particular direction. Okay, yeah. If you look at the top view of the diagram, right, you notice that the current is either coming out of the paper or going into the paper. Okay, so coming out of the paper, normally we put in dot. Okay, dot means it is out of paper. Okay, where cross is into the paper. Okay, so how do they determine whether dot or cross is in the paper? This actually they use the concept of arrow. Okay, so where a person shoot the arrow right towards the other person. Okay, so the red color person who shoot the arrow will see that the arrow is going away from him, right? So he will see a cross. While the blue color person, because the arrow is coming towards him, from his point of view, he will see a dot. Okay, so that's how they determine a dot and cross. Okay, so for the left diagram where the current is coming out of the paper, if you orientate your thumb out of the paper, you curl your four fingers, you notice that the direction of the magnetic field is in the anti-clockwise direction. While for the current that is going into the paper, you point your thumb into the paper and you curl your four fingers. Okay, so the direction of the magnetic field is in the clockwise direction. Yeah, okay, so the right hand rule is very important. Okay, so what about the side view? Okay, so same thing, your thumb is pointing in the direction of your current, yeah, and you curl your four fingers. You notice that at the left hand side of your wire, your four fingers are coming out of the paper. So that's why your magnetic field is out of the paper. That's why it's represented by the dot. While for the right hand side of your diagram, right, your four fingers are into the paper. That's why your magnetic field is represented by the cross into the paper. Okay, and the strength of the magnetic field depends on two things: the size of the current. If you have a big current, the magnetic field is also high, because magnetic field is directly proportional to the size of your current. Alright, so if you go to JC, right, if you intend to go to JC, you will learn more, right? You will learn that actually B is the magnetic field. B is equal to mu naught N I, right? So you will see that B field is directly proportional to the size of your current. Yeah. And another thing is that the distance from the current. Okay. So if you are located nearer to the current, the magnetic field strength will be bigger. Yeah. So how is it represented by your diagram? Okay. So let's go back to this diagram. Okay. You notice that when at this particular point, right? When I'm nearer to the current, the magnetic field lines are nearer to one another, right? If I go away from the current, right, at this particular direction, okay, the magnetic field lines are further away from one another. Okay, so this indicate that if I'm located nearer to the current, my magnetic field strength is higher. If I'm located away from the current, my magnetic field strength will be weaker. Yeah. Okay, so this diagram also shows the second case, right? The thing is that if you look at the dot, the distance from the dot, okay, right? So the dot is quite near to each other, right? So it means that the magnetic field lines are nearer to one another. But if you go away from the current, you will notice that the dots are further away from one another. Okay, yeah. So these two things affects the strength of the magnetic field, right? Okay, yeah. So next I want to talk about is the circular coil. Okay, so particular for circular coil, it has only one turn, okay, one turn of the wire. Okay, so so if I have a current flowing through this circular coil, this will create a magnetic field, right? So for this, not to worry, I don't think you will be tested on how to draw this type of magnetic field, okay, but you'll be tested on how to draw when you are looking at the top view. Okay, so looking at the left hand side of the diagram, right? Okay, now instead of your thumb being the direction of your current, now your four fingers will be the direction of your current. Okay, so your current is flowing in the clockwise manner, right? So your four fingers must go according to the clockwise manner. Okay, and you notice that the thumb now is pointing into the paper. So the thumb now is your magnetic field, the direction of the magnetic field. Okay, so the magnetic field will be pointing into the paper, right? So if your current is flowing in the anti-clockwise direction, in this particular case, right? So your current is flowing in the anti-clockwise direction. So your four fingers must curl, okay, curl in the anti-clockwise direction, and your thumb will be pointing out of the paper. That's why your B field or your magnetic field is out of the paper. Okay, yeah. So that's how you determine the direction of the magnetic field for circular coil. Okay. So the last thing we need to know is solenoid. Solenoid is basically just like your case 2. Okay, case 2 is one turn, but solenoid has many turns. Okay, many turns. So these many turns of wire are put together, and I pass a current through this coil of wire. So how does the magnetic field looks like in the solenoid? So if you have this, right, positive, negative, and your current will flow in this particular direction. Okay, so now same thing, your four fingers will imitate the direction of the current, and the thumb will be the direction of your magnetic field. Okay, yeah. So you notice that your thumb is pointing towards the left, right? Yeah. So how come the left is north while the right is south? Okay, isn't when I go back to my the first page, right? If I go back to the first page, right? Okay, so the north pole, the magnetic field is pointing from the north to the south. All right. So by right for this, right? By right for this will also be, this should be south, right? And this should be north, because north is the magnetic field lines is pointing in this particular direction. So by right, the right hand side should be north, but the left hand side should be south. But how come the left hand side is north while the right hand side is south? Actually, for this, right, you must treat this solenoid as the internal of a magnet. Okay, so what do I mean? Maybe I draw here. Okay, so if you have a magnet, okay, where this is north, this is south, right? Okay, we determine that the field lines goes from north to south. Okay, but for solenoid, you must treat this as the internal of the magnet. This is the external of the magnet. So you must treat the solenoid as the internal of the magnet. Okay, so if you look at the internal of a magnet, how does the magnetic field flows? Okay. Yeah, so you notice that the magnetic field inside the magnet is flowing from south to north, right? So basically, this one, right, is north. Okay, this one is north, and this one is south. Yeah, so this is how you determine the polarity, the magnetic polarity of a solenoid. Okay. Yeah, and how is the field lines being the field lines are represented in this particular diagram. Okay, and for the center of the solenoid, right, the center of solenoid, the field strength is higher. Okay, the magnetic field strength is higher as compared to the both ends. Okay, both ends of your solenoid, where your B field is weaker. So how much stronger and how much weaker? Basically, approximately, the magnetic field strength at the center is about twice the magnetic field strength at the both ends. Alright, okay, so yeah, so that's it for your solenoid.